All right, I'm going to do a few problems from the end of chapter 5. I've been doing these on these little Q&As when no one calls in. Uh, they will be posted in the Q&A. And I'm on problem 38 from the back of the book. So let me share with you what I'm about to write. So here we have a problem from page 264. You mix 125 milliliters of 2.50 cesium hydroxide with 50 milliliters of 0.625 molar hydrofluoric acid in a coffee cup calorimeter, and the temperature of both solutions rise from 21.5 degrees Celsius before mixing to 24.40 degrees Celsius after the reaction. What is the enthalpy of reaction per mole of cesium hydroxide? Assume the densities of the solutions are all 1 gram per milliliter, 1.00, and the specific heat capacities of the solutions are 4.2 joules per gram per K. So I'm going to draw a quick little picture here. So we have (125 milliliters of 2.50 molar cesium hydroxide. And you'll see that the temperature rises from 21.50 degrees, so that's 21.50 degrees before mixing, to 24.40 degrees after mixing. So here's my other container. Try and make it look the same size as that one. Since it has only 50 milliliters, I'm going to have the level right here. And I'm going to write 50.0 milliliters there and 0.625 molar HF there. And I'm going to write 21.50 degrees Celsius there. Now, when you mix the two, so here's another container that's the same size as the other two. I'm adding these two volumes together. So here's my 125 milliliters, and here's my 50 milliliters. And we know darn well that these solutions will mix, but we're going to pretend that they don't, just so we can keep track of this turning into this and this turning into this, so to speak. Now, the final temperature is 24.40 degrees Celsius. All right, so we're supposed to find out the enthalpy of reaction per mole of cesium hydroxide. The enthalpy of reaction is given this symbol in the book, delta RH. A lot of people just write delta H. So this is the enthalpy of reaction. And the triangle is pronounced as delta, because that's the Greek symbol that it is. And of course, the way you say H is H, or sometimes it's spelled this way, delta H. I know you may find it weird that I'm spelling out a letter, but dictionaries do that. Okay, so enthalpy of reaction, delta H, sometimes it's called a heat of reaction. So this guy has a lot of names. All right, and that is the heat change associated with the reaction. And a quick reminder to you, if it's an endothermic reaction, then delta H will be positive. And energy is absorbed. And if we wanted to put the energy into the reaction, it would be a reactant. And for exothermic, we have the exact opposite. Delta H is negative, energy released, and the energy is a product. And so I'm going to move the paper just a little bit to make sure that you can see all of that. Okay, now I'm going to say that energy is released because the temperature rises in both cases from 21.50 to 24.40. So here's the tact I'm going to take with this particular problem to find the enthalpy per mole of cesium hydroxide. So we want the delta H per mole of cesium hydroxide. So I'm going to tackle this first by calculating the delta H. And then I'm going to calculate the moles of cesium hydroxide that react. So I'm going to do both of these. And in this case, it's better to do them as separate problems than combine them together. So to find out the delta H, I'm going to simplify what we're looking at. So I'm going to put this sheet off to the side, and I'm going to redraw this so that we see that we have 125 milliliters and 50 milliliters, and that's 125 and 50.0 milliliters. And they're both at 21.50 degrees Celsius. So I can pretend like they both started in the same container, and somehow magically the reactants in them didn't mix. And then I snap my fingers, everything's allowed to mix, and I end up with the same container with 125 milliliters and 50.0 milliliters. And now the temperature is 24.40 degrees Celsius. So I can use these numbers to actually calculate the energy that this thing absorbs. Now, there is a change in temp. Because there is a change in temp, we're going to use Q is equal to Cm delta T. Some people memorize this as Q equals M cat, where the triangle, the delta, looks kind of like an A. I just remember it this way. So Q is the heat energy, which we will also be using as delta H, and C is the specific heat capacity of the solution, M is the mass of the solution, and delta T is the change in temperature of the solution, where we have C, M, T final minus T initial. So we were told that the solution has a specific heat capacity, if we pull this down here, of 4.2 joules per gram K. So I'm going to make a list over here of values. So the specific heat capacity is 4.2 joules per gram per K. That's the way you say that. Now, you know me, I like you to do work to show how you change things, but this is a case where you do not have to. If you watch my previous lectures, you'll see that we can substitute degrees Celsius for K. And I'm okay with you doing that on an exam or on homework or whatever, or quiz. So these are the same thing. And the reason for that is this temperature is found by getting a difference. The difference in Kelvin temperatures is equal to the same difference in degrees Celsius temperatures. So that's why we're able to do that. And the differences are exactly the same. Okay, so there's my C. For my mass, you can see that we've got 175.0 milliliters, right? So 125 plus 50.0 is 175.0, and that's going to be milliliters. So we have 175.0 milliliters, and we're given that the density of the solution is 1.00 grams per milliliter. Now, this is a case where you're going to show the calculation, 1.00 grams per milliliter. So we will have 175.0 grams of solution. Now, I'm going to put a little arrow here that points to the 5, because when I add these two numbers together, the 50 is good to the 10th, the 125 is good to the ones. The 1 is less precise than 10th. So this would be rounded to the ones, the rule for adding numbers together and carrying significant figures. So there's my mass for this formula. And for T final minus T initial, we have 24.40 minus 21.50. So I've got my units, I've got my numbers. And when I do the subtraction, 0 minus 0 is 0. 4 minus 5, I have to borrow 1, and that becomes 9. So that's now a 3. 3 minus 1 is 2. And of course, the decimal goes right there. And then 2 minus 2 is 0. So the difference is 2.90 degrees Celsius. And just like over here, we look at the precision of each of the beginning numbers. They're both precise to 2 places over from the decimal, which means this is precise to 2 places over from the decimal. So now we can calculate the Q as 4.2 joules per gram per degree Celsius. That's C. The M is 175.0 grams, but I'm going to put an arrow to the 5, indicating that I'm carrying an extra significant digit before I round. And then I have 2.90 degrees Celsius. So I'm going to put an arrow to the 0. So let's see what we get here. So I'm going to estimate the answer so that when I plug this into my calculator, I don't accidentally make a mistake. So I would say that's 3. 3 times 4 is roughly 10. I know it's more than 10. 10 times 175 should be 1,075. But since 3 times 4.2 is probably a little more than 10, I'm going to say that this isn't really 1,750. It's going to be probably more like, I don't know, 1,850. That's my ish. And let's see what we get. 4.2 times 175.0 times 2.90. And, oh, I'm kind of off there. It's more like 2,131. Now, this would be rounded to the hundreds. And so what I'm going to do here is I'm going to say that's equal to 2130 joules and put an arrow to the 1. And you can see I'm carrying an extra significant figure because I'm not done with that. Remember, if we go back and look at the setup, we need the delta H, which is Q, and we need the moles of cesium hydroxide. So now we have the delta H. Let's calculate the moles of cesium hydroxide. So to get the moles of cesium hydroxide, I'm going to use the molarity of cesium hydroxide. And we can see that we have 125 milliliters of the cesium hydroxide solution. Since molarity is in moles per liter, I need to convert that into liters. So I'm going to multiply by 1 liter of the cesium hydroxide per 1,000 milliliters of the cesium hydroxide. Now I can use this concentration, and remember, we can replace the M with moles per liter. So 2.50 moles of cesium hydroxide per 1 liter of that cesium hydroxide solution. And then we need to convert this into moles of hydrofluoric acid. Actually, I'm sorry, we need moles of cesium. We're good. So let's see what we get here. How do I want to estimate this? Well, 2.5 times 125 has got to be close to 300, right? 300 divided by 1,000 should be close to 0.3. Okay, so 125 times 2.50 divided by 1,000 is a 0.3125. And the unit are going to be moles of cesium hydroxide. Okay. And we have 3 significant figures here, 3 here, so this is good to that 2 right there. Now, the question I have is, do I have enough hydrofluoric acid to react with all of this cesium hydroxide? We can see that the ratio is 1 to 1, So I want to calculate if I have 0.3125 moles of HF or more. Because if I do have this much or more, all of the cesium hydroxide will react. So I'm going to do the same type of problem with the hydrofluoric acid, only with the numbers from the hydrofluoric acid. So I have 50.0 milliliters of hydrofluoric acid times 1 liter of hydrofluoric acid per 1,000 milliliters of hydrofluoric acid times the molarity is much different, 0.625 moles, not M, moles of HF per 1 liter of HF. So remember, when I get rid of that M, I'm not really getting rid of it. I'm substituting moles per liter for it. And here we're going to be able to calculate how many moles of HF we have. Now, the way I guess I would do this is 0.62 is close to 2/3. So 2/3 of 50 is roughly 75, 74. So 74 divided by 1,000 is going to be something like 0.074. All right, so let's see what happens. 50 times 0.625 divided by 1,000. And I did something wrong. Let me try this again. And how did I estimate this incorrectly? 34, oh, I said 34 divided by 1,000 is like 0.034. So let me try this again. 50 times 0.625 divided by 1,000. And I get 0.03125 moles of cesium of HF. Now, when I look at a problem like this and I see the big differences here between the amounts that are being used, it makes me wonder if this problem was written correctly. So let's take a quick look in the book and find out. So this is number 38 on page 264. It's easy to find it. Little page flipping. And here we go. 38, number 264, 125 mils of 0.2, look at that, 0.250. You can't see that. 0.250 molar, not 2.50 molar. So we get to correct this problem and cross this out and write 0.250 molar. And then we cross this out and write 0.250 molar. And since this number is 1/10 of that value, this number is 0.03125 moles of cesium hydroxide. Okay, so I'm glad we fixed that. Luckily, this doesn't change the volumes, it just changes the concentration. So we have precisely the amount of cesium hydroxide in HF we need to react. So to find out the change in energy, the change in enthalpy per mole, we're going to use our change in energy, which I'm going to have to grab another piece of paper here and show you or remind you that the value we got is 2,130 joules. Okay, so 2,130 joules, and I'm going to put the arrow pointing to the 1, divided by 0.03125 mole of cesium hydroxide. Okay, so this is good to the 2. So here we have 3 significant figures on the bottom, 2 on top. So that gives us 2 zig figs to work with at the end of this problem. And then we have to do one more thing. So 2,130 divided by 0.03125, and we get 6,8 joules per mole. So what is the enthalpy of reaction per mole of cesium hydroxide? This looks like the answer, except one thing. We have to remember that the water gained this much energy, right? And so we actually calculated the change of enthalpy for the water, or the Q of the water. That's what we just calculated. How do you get the Q of the reaction? Well, the Q of the water plus the Q of the reaction is equal to 0, which means the Q of the reaction is negative Q of the water. So really, we should have put negative 2,130 joules over 0.03125 moles, which gives you a value of negative 68,000 joules per mole. And that's how much energy is leaving the reaction. Where's it going? It's going into the water to heat it up. So this is a negative value. All right, so that is a very interesting problem with many facets to it. Okay, so let's put all of that away. And let's go to the next problem. Okay, so here's our next problem. A piece of chromium metal with a mass of 24.26 grams is heated in boiling water to 98.3 degrees Celsius and then dropped into a coffee cup calorimeter containing 82.3 grams of water at 23.3 degrees Celsius. When thermal equilibrium is reached, the final temperature is 25.6 degrees Celsius. Calculate the specific heat capacity of chromium. This is almost exactly what you're going to do with the specific heat capacity lab. You're going to take hot metal and you're going to put it in water and you're going to see the temperature change and you're going to calculate the specific heat capacity of water. So when we draw this out, and this is just like, I believe, problem, I want to say 16 from the book, where we did it for molybdenum. We have chromium metal with a mass of 24.26 grams. So that's my chromium metal. And it is heated in boiling water to 98.3 degrees Celsius. So when you take it out of the boiling water, it is 98.3 degrees Celsius. And it'll stay that way for a second. And you take that hot piece of metal and you drop it into a coffee cup calorimeter containing 82.3 grams of H2O with a temperature of 23.3 degrees Celsius. Now, let's stop for a moment and ask ourselves, how do you get a piece of metal to be 98.3 degrees Celsius? And the answer is really simple. They heat it in boiling water. At what temperature does water boil? Normally it boils at 100 degrees Celsius, but that is under just perfect conditions of 1 atmosphere of pressure, and it doesn't happen very often. So how do you find out how hot the metal is? You put your thermometer in the boiling water. So this piece of metal, before you take it from here, it's in a pot of boiling water. So here's my roiling water. Here's my piece of metal. And you have a thermometer in here and you measure that temperature of 98.3 degrees Celsius. Then you take that piece of metal and you quickly transfer it into the water, but you don't transfer any of this water. So what might be a good way to transfer this piece of metal into this water? Maybe a pair of tongs if it's one piece. But what if you don't have one piece of metal? What if you have a bunches of pieces of metal, like say a bunch of pennies what might you do to transfer this into here? Well, imagine if you had your pennies in a beaker. So here's your beaker, and here's all your pennies, and there's water in the beaker, and you want water in the beaker so you have good contact, and you measure the temperature of the water, and then let's say that you get it up, you get the temperature up to close to 100 degrees Celsius. You let it sit there for a while so that you make sure it stays that temp. You don't touch your thermometer to the bottom of the pan because it's going to be hotter than where the water is. And then once you get to a steady temp, you take out your beaker and you pour all the water out very quickly, and then take the pennies and drop it in your water. That could work. Okay, so when we're done here, what is going to happen is that the level of water rises because you got your piece of chromium in here, and the final temp is 25.6 degrees Celsius. That is the temperature of the water and the temperature of the chromium, both because of thermal equilibrium. So I only need to write that number down once. And that's what happens when you take a hot object and mix it with a cold object. The temperature of the cold object rises, the temperature of the hot lowers until they reach the same temp thermal equilibrium. It does help if you use a styrofoam coffee cup here so that very little energy is transferred. And what's even better is if you have a lid on it and all sorts of stuff. But you know what? We're just going to make it easy at first to see what happens. So get yourself a styrofoam cup. What kind of cups do you want to stay away from? Well, probably glass, because that absorbs a lot of energy, and so forth and so on. So we're going to assume that all of the energy from plus the energy of water is equal to 0. So that's what we get to do when these two things are in contact. You add up their energies and you get 0. Okay, so we have a nice setup here. So how do we calculate the Q of chromium, and how do we calculate the Q of H2O from this information? Okay, so I'm going to put that off to the side, and let's take a look. So in both cases, we're having a change in temp. So we would say the Q of the chromium is equal to the specific heat capacity of the chromium times the mass of the chromium times the change in temp of the chromium. Okay. Now, we're given most of this information, but not the specific heat capacity of chromium. That's what we want. The specific heat capacity of the water, I'm going to put W for water, is the specific heat capacity of water. So the Q of the water, the heat that the water gets, is equal to the specific heat capacity of the water times the mass of the water times the change in temp of the water. And I want you to recall that Q of CR plus Q of W is equal to 0. And we're assuming that all heat transfer happens between the water and the chromium and nothing else. So I think we can see that we can manipulate this and say that Q of the chromium is equal to negative Q of the water. And then we can also say that C of the chromium, mass of the chromium, change in temp of the chromium is equal to negative specific heat capacity of the water, mass of the water, change in temp of the water. And then I can divide both sides by mass of the chromium and change in temp of the chromium, and I get this. The specific heat capacity of the chromium is negative specific heat capacity of the water, mass of the water, change in temp of the water, all over mass of the chromium, change in temp of the chromium. So let's take this equation and figure out that specific heat capacity of chromium. So what is the specific heat capacity of water? You should memorize that as 1 calorie per gram per degree Celsius. What is the mass of water? We're given 82.3 grams. And what is the change in temp of the water? Well, it finishes at 25.6 degrees Celsius. So that's what we write down first, where it finishes. And then we subtract the initial, which is 23.3 degrees Celsius. So if I do the work here carefully, this has infinite number of significant figures because that is defined for water. This has 3 sig figs, and let's look at this difference. 25.6 minus 23.3. We get a 3 here and a 2 here. So we only get 2.3 degrees here with 2 zig figs because both the initial numbers are good to the 10th. So that means the 2.3 is only good to the 10th. So I'm actually going to write this out here so you can see that. Two zig figs here, 3 zig figs here, infinite here. We get 2 zig figs at the end, but we're not done, so we're not going to round yet. We're going to keep track. So I'm going to estimate this answer. I know that 2 times 82 is about 160. 3 is like 1/3. 1/3 of 82 is probably like 25. So 160 plus 25 puts my ish at 185-ish. So let's see what we get. 82.3 times 2.3 is 189. 189. Now I'm only allowed 2 zig figs for my answer here. So I'm going to put a little arrow here at the 8 telling me that that's where I should round if I were done with this problem. Okay, so I see now that I shouldn't have done all of this. What I should have done is just the following. I should have put in the mass of the chromium and the change in temp of the chromium and done the whole thing at one time. So I'm going to go ahead and do that. So I got 1 calorie per gram per degree Celsius, 82.3 grams, 2.3 degrees Celsius, all of this over the mass of the chromium, which is 24.26 grams. And the change in temp of the chromium, I'm going to do a little aside like this. We have that the initial temp was 98.3 and the final temp was 25.6. So here, the temperature goes from a high number to a low number, which is a negative temperature change. So here we have basically 3 minus 6 will give you 7. 7 minus 5 will give you 2. And 9 minus 2 is 7. So there's a 72-degree temperature change, and we put negative 72.7 degrees Celsius. Now, remember, there's that negative there, which needs to go right here. So I'm going to cross all of this stuff out, and we're going to put a little box around it and say ignore. And we're going to take this little arrow and go here instead. Ignore. Okay, so now it's even easier to see how many significant figures I'm going to get for this particular calculation. Infinite, 3, 2, 4, 3. So we get 2. So I'm going to take these numbers, multiply them together, which I said should be about 165. I can't remember what I said. Oh, 2 times that is 165. A third of that is 25, so like 190 or 180. So I have 180 divided by 24, well, actually 72.47 or 24.26. I'm going to do the 24.26. So how many times will 24.26 go into 180? About 7 times. So I have 7 divided by negative 72, which is about 1/10 or 0.1. Negative 0.1. But since this is negative, the negative of a negative is positive. So I should get about 0.1 for my specific heat capacity of chromium. What are the units going to be? Well, this gram cancels that gram. This degree Celsius cancels this degree Celsius. And none of these units cancel. So we're going to have calories per gram per degree Celsius. And let's see what we get. 82.3 times 2.3 divided by 24.26 and divided by 72.7. And we get, two significant figures. So 0.11 calories per gram degree Celsius. And that's how you figure out that specific heat capacity. Now, you want to show all of this work to get here. You don't memorize that formula. And I would like to see how you get to that formula on a test. So there you go. All right, let's put that off to the side. The beautiful part, I think, about doing this when no one's listening is I can stop anytime I want. I don't like doing books where we have problems where we have to look in the book because it's too hard to read what's in the book and go back and forth because the font size is so different. Okay, so let's take a look at this problem here and see how we do this one. So suppose you burn 0.300 grams of carbon solid in excess oxygen gas in a constant volume calorimeter to give CO2. The temperature of the calorimeter, which contains 775 grams of water, increased from 25 degrees Celsius to 27.38 degrees Celsius. The heat capacity of the bomb is 893 joules per K. Calculate the change in internal energy per mole of the carbon. So that's what that is. Now, for these problems, I generally think of the change of internal energy as delta H, or Q, more simply. So here's the way we're going to do this. We're going to set up all of our Qs. So what are the things in thermal contact here? Well, there is the Q of the reaction. So this reaction gives off energy, so it's part of the energy exchange. Now, the temperature of the calorimeter, which contains 775 grams of water, the water increases from 25 to 27.3. And we know that because if the water is in the calorimeter, they're in thermal equilibrium. So if the calorimeter starts at 25, the water starts at 25. So we have Q of the water here, plus we have the Q of the bomb. So taken together, the water and the bomb is the calorimeter. All right. So these are all the things that are sharing energy, and we say that's equal to 0. Now we want to get the delta U per mole of reaction. For all practical purposes, that delta U per mole of carbon is going to be Q of the reaction over the moles of carbon. So that's what we want to do. Okay, so how do we figure these things out? How do we figure out what's going on here? Well, for Q of the reaction, which is what we're trying to figure out for the top of this problem here, we have Q of the reaction is equal to negative Q of the water minus Q of the bomb. So we need to figure out the amount of energy given off by the water. So how do we do that? Well, Q of the water is specific heat capacity of the water, mass of the water, change in temp of the water. So let's go ahead and figure this one out. 1 calorie per gram per degree Celsius. The mass of the water is 775 grams. The change in temp of the water is going to be 27.38 minus 25. So I'm going to do a little work over here. 27.38 degrees Celsius minus 25.00 degrees Celsius. So I can see that that's going to be 2.38 degrees Celsius, good to the 100th. And it is a positive value because we start at a low number and end at a high. So if I estimate this, I know that 2 times 775 is like 1,500, 1,550 actually. 0.38 is like a third. So a third of 775 has got to be what? 250. So 250 plus our 1,550 puts us at around 1,800. Let's see what we get. 775 times 2.38, and we get 1,845 calories. This has 3 significant figures. This has 3, so this is good to the 4. So we're going to keep track of that. So that's Q of the water. Now, Q of the bomb, how do we figure that out? Well, I think it's pretty clear that we're going to have to use this 893 joules per K. But in this particular type of problem, we are allowed to change the K into degrees Celsius. So that's what we're going to start with. We know that the answer has to come out to be energy units. Here I have calories, here I have joules. So I've got to decide, do I want to change this one into joules or this one into calories? I'm going to go ahead and change this one into joules. So I'm going to put my sheet of paper up and I'm going to write Q of W is 1,845 calories times 4.184 joules per calorie. So let's see what we get here. Times 4.184, and we get 7717 joules. Remember, this is good to here, 3 significant figures. This is good to 4, so this would be good to 3. So here, this has got to end up being joules. What do I need to multiply by to get rid of that degrees Celsius? Well, it turns out I have to multiply by a temperature. So what temperature do we multiply by? The change in temp of the calorimeter, which is also 2.38 degrees Celsius. Okay, so what is 900 times 2? 1,800. What's a third of 900? 300. What's 1,800 plus 300? 2,100. So I should get around 2,100 joules here. And I get 2125 joules, 3 zig figs, 3 zig figs. So this is good to there. Now, what's nice about this is that this is good to the tens. This is good to the tens. So when we plug it into this problem up here, Q of the reaction, we get negative 7717 joules plus negative 2125 joules. And so let's add these together. And if I estimate this, basically I'm going to get 9,800 and something, right? So 9,842 joules. And we're good to the tens. Okay, now I want us to revisit what we're supposed to be doing here. We're supposed to be getting the change in energy per mole of carbon. So here's the change in energy. How many moles of carbon are there? Well, here we have 0.300 grams of carbon. So we can change that into moles of carbon very easily. So 0.300 grams of carbon times 1 mole of carbon per 12.01 grams of carbon. And here I'm going to compartmentalize everything. This is where we kind of started. This is a little aside for making the temperature calculation. This we put all together so that we could know what we had to calculate. Here, this was all to calculate the Q of the water. This was all to calculate the Q of the bomb. And this was to calculate the Q of the reaction. So right here, how many moles of carbon do we have? How many times does 12 go into 300? I don't know exactly, but it's got to be way less than 1, right? Because 0.3 is less than 1, and you're dividing it by 12. It's got to be way less than 1. You can even pretend that's a 10, so we're going to get 0.03. Now that's not 10, so it should be 0.028 or something like that. Excuse me. And I get 0.02498. 3 significant figures, 4 significant figures. So this is good to the 9 because leading zeros do not count. And this is moles of carbon. So now we can put this all together with this. And we have the change in energy per mole of carbon is going to be equal to negative 9842 joules, arrow pointing to the 4, divided by 0.02498 moles, arrow pointing to the 9. Since this is division, we look at the number of zig figs in each. This should have 3, this should have 3, so we're left with 3 significant figures. And you can see that this number is going to be quite a bit bigger than 9,842 because this number is so small. So if I did this right, I'm going to put this in scientific notation. I get 3.9 times 10 to the 5 joules per mole. And there's your final answer. And you need to show all of this work so that I know you know what you're doing. If you just throw that up at the end of this problem and it's worth 10 points like on an exam, I'd give you 1 point for getting it right, as long as you have the right number of zig figs. I don't have the right number of zig figs. I do have to have a 4 there. So 3.94 times 10 to the 5th. Okay, and that's for that problem there. So you can see a lot of these problems in this particular part of the book. You've got to be good with numbers and using your calculator and also with ideas. So it can be challenging. All right. I'm going to leave this one at that. This is another one that has that's just like the one we did. I will leave that one for you to do and see how you do. If you have a question about this one, you can always ask. And we'll pick up with 48 when we come back. All right. Thanks for listening. And you guys have a good evening.